By the end of this video, you'll have a solid grasp of how central entropy is in thermodynamics, and how it helps a lot in understanding nearly all of its various concepts. First of all, I want to introduce three important equations that we will use in this wonderful journey, namely heat, which takes both forms, where U is the total inner energy of the system, H is the enthalpy, P is the pressure, and V is the volume of the system. The enthalpy itself is given by. Then we will define the process coefficient and denote it as N. Entropy in a reversible process is defined by. To find the entropy, we should find an expression that rules the heat exchange of the system. Let's start first with the constant volume process. The index N is infinite, and the volume of the system remains constant throughout the process. If we look at the three equations above, we find that it is easier to use equation 1 because it contains dV. Since the volume is constant, we are left with. In this process, the change in heat is equivalent to the change in internal energy, because the system cannot do a PV work. For an ideal gas, heat, and internal energy is directly proportional to the temperature change by the relation, where CV represents the heat capacity at a constant volume. It's the rate or the speed at which the system's internal energy changes when changing its temperature. Now let's substitute this in the definition of entropy. The ideal gas entropy in the process of constant volume is. This now begs to be integrated between the initial and the final points of the process. We now turn to the constant pressure process. The index N here is equal to 0. Since the pressure is constant, if we look at the above equations, we would better choose the second one. In the case of an ideal gas, the change in heat is again proportional to the change in temperature. However, here we have the enthalpy, not the internal energy. Let's substitute this into the entropy definition. We integrate. The difference in the entropy between the two processes is how they get influenced by thermal transport, and this is determined by the constants Cp and Cv. Now we talk about processes of constant temperature or isothermal processes. N here is equal to 1. As soon as you know that the temperature is constant, you should immediately realize that the internal energy of the system, and even enthalpy, are both constant. Which implies we can use both equations 1 and 2. By using equation 1 we have. Let's substitute these into the definition of entropy. As we did in the previous two processes, constant volume and constant pressure, here also we want to integrate. Therefore, we must find a relationship between the variables P, T, and V. Such a relation is called equation of state. In the case of an ideal gas, the relationship is where R is the universal gas constant. It is Avogadro's number multiplied by Boltzmann's constant. So we find that. We integrate. We will get the same result if we use relation 2. In an isothermal process, the ideal gas has the important relationship. That is. Hence, this entropy can be written in terms of pressure as well. The easiest reversible process in terms of entropy calculation is the adiabatic process. It is also called the isentropic process. The entropy remains constant, since there is no heat exchange here. Besides this, we have the polytropic process. It is the most general reversible one, where nothing is constant. Everything changes. So, we need to simultaneously know some set of variables to calculate entropy. On one hand, if we knew the initial and final temperatures and the initial and final volumes, we use equation 1. There are no vanishing terms now. Plug it into DS definition. The first term is ready to be integrated. For the second one, we will use the equation of state for the ideal gas. It becomes in the form. And the total change in entropy is. On the other hand, if we know the initial and final values for both temperatures and pressures, we can use equation 2. As in the constant pressure process, here again we substitute for the enthalpy. We substitute in ds. By utilizing the equation of state of the ideal gas, Another variable that helps us in such processes is the index, n, along with the initial and final volumes. We can also calculate the entropy change, which I will introduce here. The result is simplification becomes possible if we use the famous relation divided by CV, and we get. So the previous result can also be written as Let's now move on to the irreversible process. It provides a much better description for real-world processes, because it adds something to the theory that is not found in previous reversible discussion. First, we need to define Clausius inequality of entropy over a full cycle. Entropy is a state function, also called a point property in graphs. It does not depend on the path. If we had a cycle and the processes in it were completely reversible, then entropy over the entire cycle will remain constant, because the system returns to the same starting point. An example is the Carnot engine, whose cycle consists of 2 isothermal and 2 adiabatic processes. The total entropy change of one cycle in the Carnot engine is 0. It was precisely for this system that the concept of entropy was conceived. There was a need for a symmetric quantity within it. However, if we had such a cycle, half reversible and half irreversible, then the change in entropy over the entire cycle is given by the sum. This first term is well defined and is of the reversible part. The second one is not completely unknown. Since part of the cycle is irreversible, the cycle as a whole has irreversible results. Thus, Clausius inequality applies to it. To make the cycle goes back to its starting point, the left-hand side must be 0. This only happens by adding an extra positive term. That is, we conclude from these two equations that there is some positive entropy term that always appears in irreversible processes, and is represented by S'. In other words, if we compare the integrands, the change of entropy in the irreversible case is always greater than the entropy change normally defined in the ideal reversible processes. For isolated systems, including the universe itself, the change of entropy is. But in an isolated system, delta Q is 0. That is, as we can see, the change in the entropy of a true isolated system is positive. It increases over time until it reaches the point of thermal equilibrium where entropy is at its maximum value, meaning, some significant amount of the available energy has been irreversibly converted into thermal energy, and is no more useful for performing any work. It naturally got wasted. At thermal equilibrium, entropy reaches its maximal possible value. And this is the second law in thermodynamics. Let's now consider a closed system, where it can only exchange energy with its surroundings. When in thermal equilibrium, its temperature is equal to that of that surroundings. If the volume does not change, the first law of thermodynamics gives. Where Q is the amount of heat exchanged between the system and the external world, called a heat reservoir. W is the amount of work done by the system. Since it exchanges heat with the external reservoir, the change in entropy will involve the system and the surroundings, and together are called the universe. The universe is always increasing its entropy until it reaches a state of thermal equilibrium. Hence, this last quantity is of special importance. Or in absolute terms, it's called the Helmholtz free energy. The word free here does not mean without price, as some people try to promote it, but rather means the available energy to perform useful work by the system. Note that they are associated with a constant temperature and volume. As entropy at the second term increases with time, Helmholtz's free energy gradually decreases till equilibrium, where it reaches a minimal value, and the system is no more able to perform work. The most important example in our everyday life is the relationship between the Sun and the Earth. Earth is thermally connected to the Sun. This wonderful star generates an immense amount of nuclear energy each second. This energy is released into space in the form of photons. The Sun provides Earth with low entropy, highly efficient energy. Due to the optimal distance from the Sun, liquid water can exist on Earth, allowing this energy to be utilized in various Earth processes and systems. While Earth naturally tends to increase entropy, the Sun continuously provides it with U, or high-quality energy. As a result, a balance is established between Earth's high entropic energy and the low entropic energy it receives from the Sun, allowing systems on Earth to persist for so long, especially its extremely important green cover. Now we want the pressure of the surroundings on the system to remain constant. Substitute in the second law. And once more, this quantity is highly significant in this case, and is called Gibbs free energy. Note that it's related to constant pressure. Moreover, this quantity is enthalpy. Gibbs free energy and enthalpy are linked together. Systems tend to spontaneously minimize Gibbs free energy until they reach equilibrium, and at the same time increase entropy. If the rate of entropy increase is higher than that of the change in enthalpy, the processes are entropy-driven. Meaning, the increase in entropy is the driving force in the evolution of the system. In other words, the system randomly distributes its energy on its parts and thus loses all its useful organized energy in the form of thermal energy, dissipated in this way. We say the disorder in the system increases. If the change in enthalpy is faster than that of the entropy, the system is enthalpy-driven. In other words, the process releases an amount of heat, making the system in general more condensed and ordered. If both increasing entropy and decreasing enthalpy occur at the same rate, the temperature is the decisive factor. At relatively high temperatures, entropy change predominantly drives the state. It's common in high energetic systems. Conversely, in processes at relatively low temperatures, for example chemical reactions in moderate environments, enthalpy is more significant and helps to form composite and stable products. In any case, spontaneously, the system always tends to reduce its Gibbs free energy. Don't forget to follow the channel. Thanks for watching.